In the 21st century, everyone knows what Google is and actively uses it in their daily lives. But have you ever thought about how it works? How Google decides which web page to show you first when you search for something? How does it choose the most relevant search result from billion web pages? So, at times when internet was only created, programmers needed to come up with an efficient way of giving search results, rather than displaying them, for example, in alphabetical order, which is really ridiculous to think today. The answer lies in an ingenious algorithm called PageRank. Hello, my name is Ryspek Nursultan, and the topic of this presentation is application of eigenvalues and eigenvectors in science and engineering. In my case, I'm going to discuss the use of linear algebra in PageRank algorithm, which is a foundational technology for Google's search engine and success in early 2000s. PageRank is an algorithm that ranks web pages in search engine results. It was introduced by Larry Page and Sergey Brin in 1998, who are founders of Google. So to understand how PageRank algorithm works, we need to create a visual model of a network, which is called a web graph. A web graph is a diagram that shows the links among the web pages. It follows these two rules. Each web page is a node. Web pages are connected to each other by links. So, as we can see here, these four squares represent our pages, first, second, third, and fourth, and arrows here represent how they are linked to each other. So our first page has 3 arrows, so it has 3 links. It is connected to second, third, and fourth page, and other pages follows the same rule. So as we understood what is a web graph, we can represent it in a mathematical form. To do that, we can write relationships between pages as vectors. So this is a first vector, which is a vector of a first page. Each entry of a vector represents a probability of a page to redirect to other pages. So it means that first vector has 3 values. So it means that it is linked to 3 pages, and the first value is 0 because it cannot be connected to itself. So the probability of it redirecting to other pages is 1/3, which is equal for every page here. Same goes to other pages. So here we can see all 4 vectors of our network, and combined together they can give us a matrix of the whole system of a web graph. So this is our vector named L. Each column of this vector shows the pages the current page is linked to. So for example, if we take second web page, we can see that it is linked to first and fourth web page, and the probability to redirecting them is equal, which is 1/2. If we see it in a graph, you can see that second page is connected to first and fourth page only. So it is true. And rows of this matrix show the pages current page is linked by. So for example, if we take third vector, you can see that it is linked by first and fourth page. Here is our third web page, and we have 2 arrows incoming from first and fourth web page, which is also true from this matrix. And there is one important rule in PageRank. It determines how page is considered to be important. So in PageRank, page is considered to be important and have a high rank the more it is linked by other important pages. This prevents such examples when a person can try to make his page more important by manually creating and linking a lot of fake pages to it. So as you can see here, these for web pages are fake and kinda sus. So it means that rank is directly depends not only on the number but also on the quality of the pages linked to our page. But how do we know the importance of that other web pages? So this is where a random surfer model simulation comes into play. To understand it, just imagine a person surfing on the internet who starts clicking on links at random. So, for example, I'm a surfer and I can start from any page on this network. For example, I can start from the third web page, and then the only way I can redirect to other page is to go from third page to fourth, and then I randomly go to second, first, fourth, third, again to the first, and then it continues itself many times. After many iterations, recorded data of visited pages will represent their relevant importance. So the more redirections a page has, the more it is considered to be important. To optimize this system, we can write it in a form of formula. It will make possible for computers to solve it because the real network is really big and incomparable to our web graph example. So this is our equation where x is a vector of probability distribution between pages. It shows the probabilities of ending on each page after n many clicks done by a surfer. We will see how it works in the next slide. And L, it is a matrix of a web graph that we have discussed before. So we have reached our example breakdown section of this presentation. So initial vector of probability distribution looks like this. So because we have 4 web pages, the probability of starting on each of them is equal, which is 1/4. So it is our x0 vector. And to find probability distribution and the ranks of the web pages after one click, we apply this formula, and it looks something like this, and the result will be this. So as you can see, after one click, the probability of ending on the first web page is the highest one. So the rank of the first web page is the highest according to the result we got from the one click. It is not pretty accurate because we need to do many iterations to get a final result. So we can rewrite our equation in this form. We can write this vector applying this formula itself. So it will give us something like this, and it will repeat itself until it reaches our initial vector, which is x0. So the result will be look like something like this. So I've done some calculations, and this table represents the results of these calculations, where each column represents a probability of corresponding page here, and rows represent iterations. So as we can see here, after 11 iterations, you can see that our vector of probability distribution is reached its steady state. So this may look familiar, because this is where eigenvalues come into play. Because it is clear that a final ranking of the final ranking is eigenvector of L with an eigenvalue of 1. It is crucial for this algorithm, because it makes computation process a lot easier. And even though computers are powerful, even for them, the scale of input values are just terrifying to imagine. And there is one more thing to discuss about our formula, because random surfer model we used in PageRank algorithm before is not complete yet, and a surfer is only able to jump to the pages by links, but in real world scenarios you can type any web page's address on a Google search. And this is example of this. And so it doesn't take into consideration the probability of a surfer to jump to the random page by typically typing its web address. So we need to include a coefficient called damping factor, which equals 0.85. Damping factor is a probability of a surfer to jump to pages only by links provided on the pages, and its implementation on the formula will look something like this. Damping factor is gonna be multiplied by our initial formula, and also we will add this value, which represents a probability of a surfer to address a random web page not connected by a link. So this is our final formula of PageRank algorithm, and usage of eigenvalues makes computation a lot faster and automatic. Thank you for your attention, and this is the end of my presentation.